Slowly set everything aside. Relax your body. Let yourself lie here comfortably. Take a deep breath in and slowly breathe it out. Take another deep breath in and slowly breathe it out again. Feel your shoulders loosen and drop. Feel your neck loosen and release. Feel your legs loosen and grow heavy. Your whole body is light and airy, as if you are floating in the very still, very quiet depths of space. Tonight, I will tell you a story about two asteroids, about a probe that moved forward very slowly but never stopped, about the quiet, peaceful world that lies between Mars and Jupiter, a very, very long time ago. To be precise, in 1845, humans once believed that the solar system had 11 planets. Besides the familiar Mercury, Venus, Earth, Mars, Jupiter, Saturn, and Uranus, there were four more small bodies positioned between Mars and Jupiter. These four were Ceres, Pallas, Juno, and Vesta. In that era, Neptune had not even been discovered yet, and these four tiny bodies were all regarded by the astronomers of the time as full-fledged planets. Just imagine 11 planets all spinning around the sun. Does that not sound like a lively, bustling, big family? But later scientists discovered more and more of these small bodies. They were just too small, far, far smaller than the known planets, and their orbits were highly unstable, completely different from the orbits of normal planets. As of today, the total number of asteroids we have discovered in the solar system has approached nearly 1.5 million. 1.5 million. That means this patch of sky is not just a few large planets spinning in solitude. There are innumerable tiny stones and small chunks of ice, forming a very, very long asteroid belt between Mars and Jupiter. So who was the first to realize that they should not be called planets? That person was William Herschel, the very same person who discovered Uranus. As early as 1802, Herschel had already proposed that a new term, asteroid, should be used to refer to Ceres and Pallas. He said, "They were far too small and had no right to be treated as equals with the planets." But many people at the time disagreed with him. It was only when more and more small bodies were discovered that everyone was finally convinced, for a very, very long time afterward. These asteroids were nothing but a few blurry points of light inside a telescope's view. We knew they were there. We knew they were orbiting the sun, but nobody had ever truly drawn close enough to see what they actually looked like. It was not until 2011 when the American Space Agency's Dawn probe first brought humanity up close to see the two largest bodies in the asteroid belt, Vesta and Ceres. Counting from the discovery of Vesta in 1807, we had waited over 200 years before we could finally see their true faces. Dawn was launched on September 27, 2007. Its goal was immensely ambitious: to become the first probe in human history to orbit two different asteroids, to save fuel. It also used the gravity of Mars to perform a slingshot acceleration, like being pulled by a swing, yanked forward by Mars gravity and flung in the direction of Vesta. But even with that gravitational assist, Dawn still had to fly for 4 full years before it finally reached Vesta's orbit, successfully entering orbit on July 16, 2011. 4 years of flight just to get there. Why was it so slow? It was not because the technology on Dawn was backward, quite the opposite. It used the most advanced ion propulsion engine available at the time. The principle behind this engine is wonderfully curious. A traditional chemical rocket burns fuel to produce a massive thrust, surging forward explosively, but it burns through its fuel very quickly. An ion engine is a completely different story. It uses the electricity generated by solar panels to ionize a noble gas called xenon. That is, it strips the electrons away from the xenon atoms, turning them into electrically charged particles. These charged particles are then shot out at the astonishing speed of 150,000 kilometers per hour, pushing the probe in the opposite direction. However, because Dawn could only generate a very limited amount of electrical power, the number of xenon particles it could ionize at any one time was quite small, so the thrust it produced was very, very tiny, very, very gentle. To accelerate from a complete standstill to just 100 kilometers per hour, Dawn needed 4 full days. Do you understand how slow that is? An ordinary car with one press of the accelerator can go from 0 to 100 kilometers per hour in a few seconds, but Dawn needed 4 whole days. It was like a snail crawling slowly through a garden, so slow that you could barely even see it moving. But this slowness is precisely where the ion engine's greatest strength lies. Because it consumes fuel at such an incredibly slow rate, it can fire continuously and push forward for months, even years, without stopping. On Dawn's journey to Mars, a full 85% of the time was spent firing its engine and accelerating. After consuming only 72 kilograms of xenon, it had already reached a speed of 1.8 kilometers per second. If it had been using traditional chemical fuel, achieving the same result might have required several tons of fuel, several tons versus 72 kilograms. Do you see how vast the difference is? It was precisely by relying on this slow and steady, never-give-up approach that Dawn had enough fuel to complete its historic mission of visiting 2 different asteroids. On July 16, 2011, Dawn finally arrived at Vesta's orbit and transmitted back the first close-up images, the asteroid that humans had studied through telescopes for 2 centuries. Seen up close, it actually looked just like a big potato with a very irregular shape. It was nothing like the round, spherical planet we might have imagined. Why was it shaped like a potato? There is a very important concept in astronomy called hydrostatic equilibrium. To put it simply, if a celestial body has enough mass and strong enough gravity, its own gravity will pull all of its material toward the center, tugging it into a spherical shape. It is like kneading a ball of dough. You squeeze and shape it with force, and in the end it becomes a round ball. The 8 major planets of the solar system all have more than enough mass, and their gravity is strong enough, so they are all nearly spherical. But Vesta has an average diameter of only 525 kilometers, less than 1/6 of the Moon's diameter. Its surface area is roughly the size of Pakistan. With such a small volume, its gravity is too weak. It simply does not have the strength to pull itself into a spherical shape, and so it remains in its irregular potato-like form, just spinning there in space for billions of years. Yet, even though it is so small, Vesta is still the second largest body in the asteroid belt, just behind Ceres. Its mass accounts for about 9% of the total mass of the entire asteroid belt. 9% may not sound like a lot, but think about it. The asteroid belt contains nearly 1.5 million bodies. A single asteroid, Vesta, accounts for nearly 1/10 of all that mass. From that you can understand just how important its place is in the asteroid belt. Apart from having insufficient gravity, there is another reason for Vesta's potato shape. About 1 billion or so years ago, its southern hemisphere was struck by 2 enormous asteroid impacts, one after the other. The first impact left behind a basin roughly 400 kilometers wide, called Venonea. The second impact was even more severe. It left behind a basin about 500 kilometers wide called Resilvia, the largest impact crater on Vesta. The scale of these 2 impacts is almost impossible to imagine. They directly blasted away a huge chunk of the crust of Vesta's southern hemisphere, and in the process made its already not very round shape even more deformed. Right at the very center of the Resilvia basin, the enormous energy of the impact caused the ground to rebound upward, thrusting up a mountain that rises between 19 and 22 kilometers high. For a time, this mountain was considered the tallest mountain in the entire solar system, even taller than Olympus Mons on Mars. But later, after Dawn carried out careful measurements, it was found that if you measure from the lowest point of the crater floor, this mountain is indeed taller than Olympus Mons, but if you measure it relative to Vesta's overall surface level, it does not quite surpass Olympus Mons, because Mars has a complete spherical reference surface, whereas Vesta cannot even manage to be a sphere in the first place, making any fair comparison very difficult. So in the end, everyone agreed that the title of tallest mountain in the solar system still belongs to Olympus Mons on Mars. And speaking of these two impacts, there is something truly remarkable. Scientists estimate that these two impacts excavated about 1% of Vesta's volume. 1% may not sound like much, but for a body with a diameter of just over 500 kilometers, it means an entire huge section of crust in the asteroid belt was blasted away. The ejected debris filled the asteroid belt, and some of it even fell to Earth as meteorites. Did you know that approximately 5% of all meteorites on Earth actually came from Vesta? Scientists have given these meteorites a name. They call them HED meteorites. How can they be so certain that these meteorites came from Vesta? Because the spectral characteristics of these meteorites are highly consistent with the spectral characteristics of Vesta's surface, as measured by Dawn, so consistent they are almost an exact match. In other words, certain meteorites that you might see in a museum here on Earth, their original home is on Vesta, hundreds of millions of kilometers away. After billions of years of drifting through space, they eventually fell to Earth and were picked up by human hands. These two impacts were not just enormous in scale, their depth was also staggering. Spectral data from the Hubble Space Telescope revealed that the spectral signature of olivine was detected at the bottom of the impact craters. Olivine is a classic marker of the mantle. That means these two impacts punch straight through Vesta's crust, all the way down to the mantle, bringing material from deep within the mantle directly up to the surface. Some fragments may even have fallen to Earth, allowing us to hold in our own hands a piece of another world's mantle. Judging from the data collected by Dawn, Vesta is truly special within the solar system. It is very probably the only surviving original planetary embryo in the entire solar system, a baby planet that never got the chance to finish growing up. According to modern theories of planet formation, when the solar system had just been born, the whole system was a vast, enormous cloud of gas and dust called the protoplanetary disk. Inside this disk, countless dust particles slowly clumped together, forming thousands and thousands of planetesimals. These planetesimals continuously collided and merged with one another, like rolling a snowball bigger and bigger until it finally became the large planets, Earth, Mars, Mercury, and Venus. Vesta, too, was originally on its way to becoming a full-fledged planet. It had already taken shape 4.5 billion years ago. At that time it had a molten mantle, active geological processes and heavier elements inside that were sinking downward and forming a metallic iron core, roughly 220 kilometers in diameter. Its structure was very similar to that of a true planet. You could say it was already a planetary embryo with a fully formed inner core, but then, around 1 billion years ago, two successive devastating impacts shattered its nearly completed outer shell. From that point on, it could never again achieve hydrostatic equilibrium. It would never become a planet, nor even a dwarf planet. Its iron core slowly cooled and solidified, and eventually died. From that time onward, Vesta has remained just the way it is now, spinning alone, endlessly, in the asteroid belt. Some scientists also think that it may not have been impacts alone that prevented Vesta from growing. Jupiter's influence may have played a role as well. The asteroid belt lies between Mars and Jupiter. Jupiter is the largest planet in the solar system. Its mass is over 300 times that of Earth. As Jupiter was forming, It used its enormous gravitational pull to snatch away vast amounts of material that might otherwise have gathered around Vesta. It also disrupted and stirred up the entire environment of the asteroid belt. Next to the absolute giant that is Jupiter, Vesta never stood a chance of gathering enough material to grow into a full-sized planet. Dawn also discovered many other interesting surface features on Vesta. Its youngest impact crater is called Marcia Crater, and it is about 70 kilometers in diameter. On the floor of this crater, Dawn discovered a very curious type of terrain called pit floor terrain. Countless densely packed tiny holes covering the entire crater floor. This kind of terrain had previously only been seen on Mars. Scientists believe that these tiny holes were formed after the impact, when the water content inside the impacting meteorite was instantly heated and vaporized by the extreme temperature of the collision, and the steam blasted these little holes into the surface. This Marcia crater also has a delightful identity. It is part of a feature known as the snowman craters. The snowman craters are made up of 3 craters of different sizes, strung together nose to tail, forming a shape that looks just like a snowman. The top circle is the head, the middle one is the body, and the bottom one is Marcia crater, forming the base of the snowman. This entire snowman is simply printed there on the surface of Vesta, having existed in silence for hundreds of millions of years, across the equatorial region of Vesta. There are also many parallel troughs and valleys. The largest of these is called Devalia Fossa, with a full length of 465 kilometers and a width of about 20 kilometers. How long is 465 kilometers? The straight-line distance from Hong Kong to Taipei is about 800 kilometers. This trough is more than half of that distance in length, and it is much bigger than the Grand Canyon of the United States. Yet the entire diameter of Vesta is only 525 kilometers. That means on an asteroid smaller than 1/6 of the Moon, there is carved a scar that is longer than the Grand Canyon on Earth. Another large trough is located in the northern hemisphere, called Saturnalia Fossa, with a length of about 370 kilometers and a width of about 40 kilometers. Dawn only stayed at Vesta for about 1 year. In September 2012, it left Vesta's orbit. It fired up its very slow but very persistent ion engine and set off toward its ultimate target, Ceres. At that time, humanity's understanding of Ceres was actually very, very limited. Even the most advanced Hubble Space Telescope at the time could only capture images of Ceres that were a total blur, nothing more than a gray, hazy, circular speck of light. So scientists placed extremely high hopes on Dawn's journey. Their only worry was that Dawn's electrical power was no longer in the best shape, and nobody knew if it would be able to hold out until the end of the mission. After more than 2 years of long flight, on March 6, 2015, Dawn successfully entered orbit around Ceres. As the probe drew closer and closer to Ceres, the resolution of the images it sent back grew higher and higher. The details of Ceres' surface slowly began to reveal themselves before the eyes of humanity. The most attention-grabbing feature was a number of very bright, very white spots on the surface of Ceres. At first, from far away, they just looked like a single tiny white dot. When Dawn got a little closer, it became clear that it was not just one spot, but 2. Get even closer, and there was actually a whole field of white spots scattered across the floor of an impact crater. Against the dark gray background of the surface, they looked especially bright and especially mysterious. What were these white spots? Why were they so bright? Could they be ice or salt? This question filled scientists all over the world with intense curiosity. Ceres is the largest body in the asteroid belt, with a diameter of 940 kilometers, roughly 1/4 of the Moon's diameter. Because its mass and gravity are both sufficiently large, It has the ability to pull itself into a spherical shape. For this very reason, Ceres is the only body in the entire asteroid belt classified as a dwarf planet. Like Pluto, it holds the status of a dwarf planet, only it is much smaller than Pluto. But the most special thing about Ceres is not its size, it is the enormous amount of water stored within its body. Most asteroids are like Vesta, dry, composed mainly of rock and metal, but the composition of Ceres leans more toward that of a comet. Comets are the great ice balls of the solar system, with ice as their main component. Ceres lies somewhere between rock and comet. Although the surface of Ceres is rocky, the rock is filled with countless pores and fissures, and tremendous amounts of water are locked inside all those little cavities. Its crust is roughly 90% rock and 10% water. Beneath the crust lies a slushy, mud-like mantle, and beneath that the inner core is a mixture of water, rock, and clay. The whole of Ceres is like one huge, freezing cold mud ball slowly spinning through space. Scientists estimate that the water content of Ceres accounts for 50% of its total volume. Half of it is water. Just think of that. The total amount of fresh water it contains may exceed all the fresh water on Earth combined. A dwarf planet with a diameter of only about 900 kilometers may hold a water reservoir richer than the entire Earth's. So what exactly were those bright white spots we saw earlier? The answer is cryovolcanoes. A cryovolcano works somewhat like a regular volcano on a planet, but what it erupts is not molten rock. It is an icy cold mixture of salty water along with ammonia and other volatile substances. The largest of the white spots is called Bright Spot 5. It sits at the very center of the Akator crater, a genuine real cryovolcanic vent. Using the data from Dawn, scientists have even constructed a three-dimensional model of this cryovolcano. Because the water on Ceres contains large amounts of salt, when the cryovolcano erupts a salty water mixture onto the surface, the water slowly sublimates, meaning it turns directly from a solid into a gas, skipping the liquid phase altogether. After sublimation, the salt is left behind on the surface, forming a reflective crust of salt. This salt crust is especially good at reflecting sunlight, which is why it looks so bright and so white. But these bright white salt crusts do not last forever. Under the prolonged bombardment of the solar wind and cosmic radiation, they slowly darken over time, eventually blending seamlessly into the surrounding gray surface. So the bright white spots we see today are only the newest and most active cryovolcanic vents on Ceres. Scientists believe that Ceres once had many more ancient cryovolcanoes. It is just that the salt crusts they left behind have long since darkened, and we can no longer see any trace of them. In addition to the cryovolcanoes, Dawn also found traces of water elsewhere on Ceres. Because the tilt of Ceres' rotational axis is very small, only about 4 degrees, it spins almost perfectly upright, not at an angle like Earth's 23.5-degree tilt. Because of this, some crater floors at the poles of Ceres never see sunlight, with no sunlight reaching them. The temperature there is extremely low. The water ice at the bottom of these craters barely sublimates at all and can remain preserved for billions of years. This situation is very similar to the poles of the Moon. At the lunar poles, there are also craters that never see sunlight, and the water ice at their bottoms has also been preserved for billions of years. Someday, when humanity needs to mine water resources in space, both the craters at the lunar poles and the craters at Ceres poles could become very important water supply bases. On Ceres, there is one especially distinctive mountain called Ahuna Mons. This mountain is about 20 kilometers wide, with an average height of 4 kilometers. Its highest point reaches 5 kilometers, making it the tallest mountain on all of Ceres. It is also so far the closest cryovolcano to the Sun ever discovered by humanity. The strangest thing about Ahuna Mons is that it stands all alone, rising straight up from a vast plain. Its position is right next to Ceres' largest impact crater, a crater called Kirwan Basin, about 284 kilometers in diameter. But aside from this crater, the area surrounding Ahuna Mons is completely flat plain, stretching endlessly in all directions. On all of Ceres, there is only this one mountain of this size. There is no second one. If there were other similar mountains on Ceres, it would not seem so strange. It could be explained as the result of some global geological process. But the fact that there is just this one, lonely, solitary mountain on the entire body, how could it have formed? The most reasonable guess at present is that its formation may be related to a large impact on the opposite side of the body. Scientists speculate that a very long time ago, a giant meteorite struck Ceres at the site of the Akator crater. The seismic waves from that impact traveled through the entire interior of Ceres and reached the far side of the body. When that energy arrived on the opposite side, it pushed the crust upward, and that is how Ahuna Mons was formed. Although Akator crater and Ahuna Mons are not exactly antipodal, an impact of this scale could indeed trigger planet-wide seismic waves with energy propagating across the entire body. October 31st, 2018. This was the day the Dawn mission came to its end. Its propellant was finally exhausted. It could no longer adjust its attitude. It could no longer send any data back to Earth. But Dawn's fate had actually been sealed from the very beginning. Although the ion engine was extremely fuel efficient, fuel will always run out one day. Fortunately, before completely losing contact, Dawn had already successfully completed all of its planned scientific tasks. It had even exceeded the space agency's expectations. The data it transmitted back will allow scientists to carry out research for decades, or even longer. To honor this brave probe, the engineers left Dawn in a stable orbit around Ceres. According to calculations, it will remain in this orbit for at least 20 years and possibly even longer. It will keep circling Ceres like a tiny artificial satellite, silently watching over the dwarf planet it spent the final years of its life exploring. When Dawn finally went dark, it did not crash onto Ceres' surface and cause contamination. Instead, it stayed quietly in its orbit, because scientists were worried that if Dawn fell onto Ceres, it might contaminate any organic material that could potentially exist there, affecting the accuracy of future research related to the origins of life on Ceres. So they chose a very gentle ending to let Dawn drift slowly in its orbit, becoming an eternal guardian moon of Ceres. Even though the Dawn mission is over, its influence is only just beginning. The ion propulsion technology it advanced has now been widely adopted across a variety of space missions. The Starlink satellites from SpaceX China's Tiangong space station, the European Space Agency's Bepicolombo probe heading to Mercury, and the American Space Agency's Asteroid impact test mission, all of them use ion propulsion technology. Dawn is like a seed, scattering this technology across the entire solar system. Even more importantly, Dawn brought us up close to see two completely different worlds. One is Vesta, a dry, rocky body with a metallic iron core, a planetary embryo that never had the chance to finish evolving. Its fragments are scattered across the solar system, some even having fallen to our Earth and become meteorite specimens held in human hands. Every piece of meteorite that came from Vesta carries within it the secrets of the solar system's birth 4.5 billion years ago. The other is Ceres, a water-rich ice rock hybrid with cryovolcanoes still quietly erupting on its surface, and a reservoir locked deep underground that contains more water than all the fresh water on Earth combined. Inside the perpetually dark craters at its poles, Primordial water ice from billions of years ago is preserved, quietly waiting for the future exploration of humanity. One is a dead planetary embryo. One is a dwarf planet that is still geologically active. One is dry and shattered. One is wet and whole. Two worlds, two fates. Yet both of them dwell in the same asteroid belt, circling the same sun, spinning for billions of years. And what connected these two worlds was a slow, steady ion engine. It took 4 days to accelerate from 0 to 100 kilometers per hour, but it persevered for 11 years, flying across hundreds of millions of kilometers of pitch-black space to let humanity see sights that no one had ever seen before. Sometimes moving slowly is not necessarily a bad thing. The most important thing is to keep going, one step at a time, one day at a time. One day you will arrive at the place you want to go. Now slowly relax your entire body. From the very top of your head all the way down to the tips of your toes, everything is fully relaxed. Imagine that you are floating in the quiet asteroid belt. All around you is the soft, gentle light of distant stars. Far away, Vesta spins slowly in the darkness, shaped just like a big potato. On the surface of Ceres, the white, bright spots glow faintly like tiny nightlights in the dark. You feel your whole body becoming very, very light. All your weight has disappeared, just like the dawn probe. You are drifting slowly through this gentle, starry sky. This universe is very, very vast, but it is also very gentle. Billions of stars twinkle and shimmer, billions of asteroids move quietly along their orbits. And we, here in the embrace of this starry sky, slowly, slowly, slowly drift off to sleep. Breathe slowly. Sleep well. Sweet dreams.